Okay, so the next topic for optics are thin lenses. So thin lenses, there's two types. We have converging lenses and diverging lenses. Now where do these guys get their name? It's very simple. Here's where they get their name. If parallel light rays, which would be like, light rays from a distant source. So here we have parallel light rays coming into this converging lens. What does the converging lens do to the parallel light rays? Makes them converge. The parallel light rays hit the lens and they converge to a point. And guess what this point is right here? That point is the what? That's the focal point of the lens. Okay, diverging lenses get their name because when parallel light rays hit a diverging lens, the light rays diverge. Okay, now you've probably seen on the practice AP exams questions that look like this. Raise your hand if that looks familiar to you. Yeah, they like to ask this. So the characteristic of a converging lens, what do these three have in common right here? These three are all converging. They are thicker in the middle and skinnier at the ends. That's the shape of a converging lens. Now, what do these guys have in common? They are skinny in the middle and thicker at the ends. So just know the general shape, converging and diverging. Okay, now equations. So in this lecture, we're going to be going over how to solve lens problems mathematically. All right, now here are your equations. Now what's real nice about this? The thing that's super nice, these equations should look familiar because they are the same equations that you used for mirrors, right? Now, the one key difference is with the sign convention for image distance. So I have a summary here, sign conventions for lenses right here. Now you'll notice it's pretty much the exact same thing that you did for mirrors. What was the sign convention for mirrors? It was super simple. Front side positive, back side negative. And remember, that does not apply to the magnification equation. The magnification equation has its own sign convention. If your magnification comes out plus, that means the image will be upright. If the magnification comes out negative, that's inverted. Okay, so for mirrors, which we did yesterday, front side plus, back side minus. Now I just want to draw your attention to one thing. This is the only tricky thing when it comes to sign convention for lenses. The sign convention for the image distance is reversed. If you're doing a calculation for where the image forms and your image distance, your SI, if your SI, which is the image distance, comes out negative, what does negative mean? Negative means in front, positive means in back. It's reversed. But everything else is the same, right? Look at object location. A positive object distance is in front. A negative object distance is in back. Okay, now, converging, diverging. So it's the same exact thing as mirrors because look, what do concave mirrors do? So the focal length yesterday when we talked about mirrors, so here's a concave mirror, right? Concave mirrors, what's the focal length for a concave mirror? Plus or minus? Plus, because why? Where's the focal length for a concave mirror? It's in the front, right? Now what do concave mirrors do? Well, when parallel light rays hit a concave mirror, so here's parallel light rays, what are these parallel light rays going to do when they strike the mirror? They're going to converge to the focal point. Oops, I should have moved that there. There's the focal point. They converge. So check it out. Converging mirrors, also called a concave mirror, have a positive focal point, have a positive focal length. Converging lenses also have a positive focal length. Okay? And then look, a convex mirror is like this. So and the focal point's back here, right? There's the focal point. When you're doing a convex mirror problem, you got to make the focal length Negative. Why does the focal length have to be negative? Because where does the focal length sit? In back. So look, what do parallel light rays do when they strike a convex mirror? So the parallel light rays come in. What do? They're going to diverge. So convex mirrors, which you could also call a diverging mirror, negative focal length. If you're talking about a diverging lens, it's a negative focal length. I don't know if that made any sense. I'm drawing a similarity between mirrors and lenses. Now, do you want to know the way I first memorized this? I'm going to give you the best trick ever. Here's the best trick ever. Dudes, if you had to choose, would you rather be conned or die? Which one of those would be more negative? Dying. You're like, oh yeah, I don't want to die. That's negative. Con me, I'll call that positive, right? You might be like, well, Spaldo, being conned is pretty negative. Oh yeah? When you put that next to dying, oh yeah, dying's more negative. Okay, all right. Dude, that was, hey, I invented that little memory trick like 20 years ago. Diverging, ooh, die, negative. That's negative. Just remember that. Die, negative. Con me any day, but don't make me die. Got it? All right, so let's do a problem here. Okay, so here's an example. We have a converging lens. Hey man, converging lens, is this going to be positive focal length or negative? Positive. Con me, but don't make me die. That would be positive focal length, okay? So take like, I don't know, you should be able to solve this in like 3 minutes. So you're using the equations from the previous screen. Give you 3 minutes. Here's how you solve this. So look, I'm going to summarize all the info. Shh. Here's the information we have. So focal length, positive 50 centimeters. Now, hey, just for funsies, you don't need this, but if they asked you on the test what the radius of curvature is, what's the radius of curvature? It'd be the same exact thing. I'm sorry, same exact thing as for mirrors. The radius of curvature is always double the focal length, just like for mirrors, same thing. Okay. Notice I made these positive converging lenses have positive focal lengths. And look, if the problem you're doing is a diverging lens, they're not going to tell you it's negative. They're going to say, all right, so this is a diverging lens, the focal length is 50, and you got to go, oh, diverging, make that negative. You know, you have to know how to do the sign conventions. All right, object distance. So with here, you know, this is a diagram that would kind of fit the situation. So the object distance is the distance from the lens to the object. That's 1 meter, positive 1. Image distance is a question mark. Magnification is a question mark. Height of the object is 8 feet, right? HO, this height right here is the height of the object. Height of the image is a question mark. So let's do the calculations. Yes, put it right there. All right, first question. Where will the image appear? So you're using this equation. 1 over SI plus 1 over SO equals 1 over the focal length. So we're looking for the image distance, which is SI. So 1 over image distance equals 1 over focal length minus 1 over object distance. So this is 1 over, so the focal length, now we want to punch this in as 0.5 meters so the units match. So 0.5 meters minus 1 over the object distance, which is 1 meter. So what this gives us is 1 over image distance. This is going to be 2 minus 1. So 1 over SI is 1. So what must SI be? The image distance comes out as positive 1 meter. Now, what does it mean if your image distance comes out positive? What's that telling you? Front or back? That's back. For lenses, if you get a positive image distance, positive is backside. That's like the image distance sign convention for lenses is like the one tricky thing to memorize. Just remember it's like the one thing that's reversed. Otherwise, everything for mirrors and lenses is front side plus, back side minus. Okay? So we figured out that the image will be 1 meter in back. Okay? And look, let's go back to the original here. So look, isn't that what we found here? The object's here, the image is there, it's on the back side, right? Okay, magnification. Magnification is negative SI over SO. So negative, our image distance came out as positive 1 meter, and then the object distance was 1 meter. So the magnification comes out as negative 1. What is this telling us? What does that negative mean? Inverted. See right here? That's what we get. Now you guys, at this point, you don't know how to do ray diagrams for lenses yet. This right here is the ray diagram, which I'm going to be going over with periods 2 and 3. So you'll have to watch that video at home. But look, a ray diagram and your calculations should agree with each other. If what you calculate does not agree with the ray diagram, then something happened. Okay, so everything agrees so far, right? So this was the image distance. I'm sorry, the object distance was 1 meter. We found out that the image distance was 1 meter in back, right? That's what the ray diagram's showing. The magnification is negative, meaning inverted. And then what does the 1 mean? Image will be same size as the object. If you multiply something by 1, it stays the same. All right, so the size of the image, look, object was 8 feet, magnification was 1, so the image will also be 8 feet. Okay? And then is image upright or inverted? It's inverted.